Alrighty. Okay, so deuterium undergoes fusion according to the following reaction, right? Identify the particle X. Well, you can do this. You're just balancing, right? So 3 plus what equals 4? There's a total of 4 on this side, right? So you can figure that out, right? And then 1 plus 1 equals 1 plus... I actually got this one wrong. I'm kind of embarrassed. Okay, but you'll get it right, okay? The following data are available for binding energies per nucleon, okay? Deuterium is 1.12, so that means, by the way, 1.12 times 2 of those, right? Okay, determine an MeV, the energy released, right? So on the left side, our binding energy, it's going to be the difference in binding energy, basically, right? We're going to something that's more tightly bound, right? So our left side, we've got total binding energy of 2 times 1.12, okay? Because we got one of these and one of these, right? And each one of those, there's 2 nucleons in a deuterium, right? So since this is binding energy per nucleon, the energy of one deuterium is 2. This is because it's 2 nucleons, right? A equals 2. And then this 2 is because there's 2 of them. There's 1, 2 of them, right? Okay. So that's going to be what, 4.48, right? And then the binding energy of this guy is, well, the binding energy per nucleon of that is 2.78, right? So the binding energy of the right side is just this, and this has no binding energy because it's not bound to anything, right? You'll figure out that it's a proton, right? I guess that it was a neutron, but that guy's a proton, right? So our right side is going to be 3 times 2.78, right? Which is much more tightly bound, right? I think you get like 8.34, right? And so the energy released is the difference in this binding energy. Now, notice that the right side has a bigger binding energy, right? That doesn't mean that it's got more energy. It just means it's more tightly bound. It's further down into that well. Binding energy is energy, not energy you have, but energy that you need to tear it apart, right? So the bigger the binding energy, the more tightly bound it is, and the lower the potential energy is. It's kind of a reverse energy, right? Okay. Really, we should, make it negative, but we don't. Okay. So, and you'll get something like if you subtract those two, this minus this, you'll get something between 3 and 4, right? Suggest why for the fusion reaction to take place, the temperature must be very high. Well, this is positively charged and that's positively charged. In order to get them close enough, and how close do you have to get them? Well, you have to get them on the order of 1 times 10 to the minus 15th meters apart. Remember that they're going to repel each other. They're going to naturally electrostatically repel each other due to the Coulomb force, right? And so the temperature has to be really high because high temperature corresponds to high velocity, high kinetic energy, therefore high velocity. And those particles have to be going fast for them to get close enough to interact using the strong nuclear force and bind to each other, okay? They have to get very close and they have to be going very fast so that it's kind of like bumper cars, All right. Okay, particle Y is produced in the collision of a proton with a kaon minus in the following reaction, right? The quark content of some of the particles involved are this, right? Now, what you got to realize is that the K plus is an antiparticle of this. So the K plus, its composition is up anti-strange. Okay, these guys are antiparticles of each other, and I missed that, so I didn't get that right. Okay, so identify for particle Y what the charge is, right? Well, take a look. We've got a minus and a plus, right? So minus and a plus on this side. And then we've got a 0 and a plus, and then decide what is that? Yeah, okay. So determine what the charge is, right? Well, I think you can do that, right? A minus and a plus add to 0, so what adds to a plus to make 0, right? And then identify the strangeness of it, right? Okay. Well, is strangeness. We can do that, right? So on the left side, we have a strangeness. Oh, this is a strong interaction, Notice that we're creating hadrons, right? So we are getting these guys close enough that there's a strong interaction. So strangeness is conserved. Okay, whenever you create hadrons, you're going to conserve strangeness, as long as it's not a decay that's creating them. Okay, if they're being created by, like, we're going to slam them together, right? That's a strong interaction. Okay, so let's figure out the strangeness of this thing. Okay, the K minus has a strange. Remember, the strange has a -1 and anti-strange is +1, right? So the left side has a -1 strangeness, right? Protons have 0 strangeness, and then the strange quark in that is -1, right? On the right side, we've got the K0, which is anti-strange. That's +1, right? And then we've got the K plus, right? Which, if you figured out it was the antiparticle of this one, which you'd have to figure out, right? Okay. Then that's also a +1, right? And then, so what do we have to add to 2 to get -1? And the answer is, I'll let you figure it out. Right? Okay, so strangeness would have to be conserved for that. All right. Is that it? I think that is.